So this is the second tutorial we're gonna do for the series of tutorials on the content of this GitHub repository. And so basically, we're gonna start, or we're gonna continue where we left it in the previous tutorial, and that is after we have generated all the data for the simulations, for the lamp simulations. We ended up here with all these folders with the data and the log lamp output files from the terminal. And so the next thing we need to do is get into post processing. And so we have the data gathering and then the Birch-Monahan feed, which we're gonna cover here. And then after that, we have all the thermal quantities calculation, like internal energy, free energy, divide temperature, and all that. So it's gonna be decent more tutorial. But so once we got to here, we're gonna go to the GitHub repository and then to post processing and then data reading on Birch-Monahan fit. We're gonna get this file over here, the data readings, energy script. We're gonna download it, then downloads. We're gonna take it to whatever folder we are running our simulation, and then we're gonna go to Spider and open it here. Right? And so basically, what this code is gonna do is that it's gonna go inside each of these directories here, and it's gonna get the energy value for each of the simulations folder, right? And it's gonna get the energy value in the lamps file. It's gonna open all the log lamps file, and it's gonna extract these two values over here, depending of which parameter you specify, right? So on the code, the only things we really need to modify are here in this part. That is the value we want to start reading, the vanadium composition. This is just for labeling, but in this case, it's for clarity, right? I think we're gonna leave it at 0.5. The time step we want to read first, which in this case is 500, and this is very important. The line location of the energy value we want on the log lamps file, which I'm gonna explain later. Where it is, right? And so, or how this works. And we're gonna hit run, and then as I said, we get the data points we need, right? We're getting for each of the simulations we held, and actually we're not getting all of them. Let me get all of them here. These are all the data points we generated one now. And so the reason why, for example, I had it before, like in just read the first 25 points, is that you can see that really the minimum energy error thing is gonna be here, right? And at some point, the potential when we like as we go further from the equilibrium positions, the potential in the simulation are actually gonna get worse. Like you can see how you get like this sudden jump, which means that like the potential in the simulation is not really capturing with the physics well. So that's why, for example, if I run like the first 25 or so, I get a much cleaner version of data, which I can later give to the Birch-Monahan feed, which we're gonna talk about in a moment. So what this means, this line number data, and which is a parameter we're gonna be passing or changing, is that what this code is really doing is that it's taking one of these log lamps files and it's basically numerating it. Like it's reading it and it's giving like it's separated line by line each of these things. It's just a Python script managing function, like a text managing function. And so, for example, you can see like line 0 is here, and then line 1, line 2 units metal, all the way through get like through the rest of the file, which to the whole of the file, which in this case has 141 lines. And you can see 141 corresponds to this part over here. So what we need to do is actually like see here in the terminal and find what line number we actually need to get the information from in our case specifically, right? Because as we changed like things like the input file, I don't know, system specifications, something in lamps itself, uh, we're very likely to get like a different line numbers or line arrangement, really. So this is something that can change pretty easily, like maybe 10 line, something like 10 lines or so. I mean, obviously, if you don't change absolutely anything, it's gonna stay the same. But as you like get to do your system or anything, like it will not work anymore because for example, it will try to like convert, I don't know, like line 102, and then like there's no number to get that from, so it's gonna throw errors, and this is gonna be pretty common. So, but in this case, this is the one we need, right? And now in our case, we're taking the values for 500 time step, the energy values, and then the 1000 values. Those are the ones we are really printing. So what I'm gonna do is that I'm gonna change this for leaving probabilities purposes, the 1000, and then 1000 is the next line, which is 108, which you can see here. So 108. Now we get the data for 1000. As you can see, it's slightly different. It's not that different, really. And again, if you wanted to get all the data, you see how it looks like it gets all the way to here. If we get 25 points only, we're only getting this part, which is better because it will lead to a better fit on later on, which we're gonna cover. But yeah, just as an example, let's see what happens if I just, I don't know, say 50 or something. You see, it's throwing an error because in this case, line 50 here, line 50, it didn't have like it wasn't able to get the item in the fourth position in like the index, the element, because there's not like there's just one word, the next character line. So there isn't really it's trying to index something that like lays out of range. That's what I say. But yeah, this is something that needs to be changed manually. Uh, and something to say is that it could you could say like, oh, this could easily be automated. Like what do you need, like do it manually, like for 500 or for 1,000? Well, I mean, that's the case if you like, if your potential works like super well, like go for it, because that means you don't have to do like manual tuning of these things. But in our case, we do need to get like the good data points that are close to the end, because our potential is not super accurate if you as you like uh, go out the boundary values for like what's actually the actual address parameter of the system. So we decided to keep it like that. I mean, if your potential is like super good, like go for it. But yeah, sometimes it's better to keep some degree of manual part, so you can actually get a feeling what's going on in the data. But yeah, once we're done here, we're gonna see we got created these two things: the 500 times steps value, and then the times the 1000. Yeah, yeah. It's just the part we want. Yeah, well, a little more, but that's fine. Maybe I'll repeat the 1001 with a little less. 22. So we get it better. Oh, so we get it safe again. Okay, that should be good. After that, we're gonna go to like GitHub again, and then we're gonna download this thing over here. Where's Morahan? Again, downloads, pick it to whatever you need it. And so now we're actually gonna get the values, like the actual properties of the thing. Um, and so the only thing we really need to change here is the composition, so you can actually read the values, these Excel files here, which in this is 0.5, so it should be able to run it. And then here is predetermined to get like 500 and 1,000, but obviously that will depend on your case specific. So this will be really the only part that will be changed, or in case you have, let's say, more values. So I'm gonna click run, and you see how we get this fit, like based on the virtual Warhammer question as we were talking about, and then we get a volume versus energy, and then the system tries to create like the fit, and then finds the bulk modulus, the Lattice parameter, and also the free energy per atom here, as well as the errors, like the errors of each of these quantities. These are the quantities you get directly out of the Birch-Morahan fit, which is bulk modulus, Lattice parameter, the derivative of the bulk modulus, and the internal energy per atom. But for example, in this case, we can see how like these two data points are like completely misleading. I mean, if it's like a better potential, a better simulation, they'll be here, but they're not. So you're getting like wrong physics, getting in and getting your simulation. So what we can do in this case, we can just do like delete them manually, And I'm pretty sure they are on the last two 500 ones. See, you see how this is like now we have a better feed like to the data, like to without like outliers or things that are really taking our simulation. Again, like just because our potential is not good in potential, it's not gonna work like in regions upper from here. Let's say that it's just not gonna capture it. So that's why we like selecting the correct boundaries is critical for when the simulation work. So we get like a continuous data points, and again you get a better fit. And you change like it actually changed things in. It's just printing a lot of stuff here, but the previous bulk model's value was 171, and now it's 157. So once you get to this point, we're kind of over for the first part of post processing. So I'm gonna cover the other calculations in the next tutorial. Just final thing from the Birch-Morahan code and the output values, we get this CSV file with the decomposition, and we have the value and the error for internal energy, volume, bulk modulus derivative, and lattice parameter here. But yeah, that'll be it for story.